Hi, this is Richard Hall, and we're going to be looking at the night sky that we have in this fabulous Wairarapa area. And some of you I know on TV, so we're going to have some lovely pictures going as well. So we'll start those off now. There we go. Okay. Anyway, so with the night sky tonight, we're going to be looking at a whole series of things. First of all, I'd like to say thanks to Dan Broughton, who always supports these programs. And what we're going to be looking on the program tonight, first of all, the realm of the giant. And the giant is actually the giant planet Jupiter, which only last week we came to our closest point to Jupiter in the sky. So it's a big, bright, brilliant object out there. After that, we're going to be talking about Olbers paradox. And then finally, we're going to be talking about the winter star date that we've got coming up. Okay, so let's start off, of course, first of all, with our realm of the giant. Okay, right. Now, if you go out in the evening, just after sundown, the first bright star-like object you're going to see is the planet Venus. That's that big, brilliant star that you can see out towards the west. And it's often called the evening star because we only ever see Venus either just after sunset in the evening sky or just in the dawn twilight. So there's Venus up there. And of course, at this time today, we've also got a first quarter moon sitting in the sky as well. So that's the moon that you can see up there as well. Now, as it begins to get dark, you'll notice that the moon itself is sitting over a curious pattern of stars, which we call the sickle. And indeed, in Europe, of course, you're looking at these stars upside down. In Europe, they'd be around the other way. The sickle was an important group of stars because when it rose up in the dawn sky thousands of years ago, it told the people it was time to bring in the harvest. So that's the sickle there, which is actually part of the constellation of Leo the lion as well. So there's a sickle in the sky. And then if we turn around to look to the south, after Venus has set, you'll see this big brilliant star up there in the east. And that's in fact the planet Jupiter. And the only cool thing with planets and that, and so first of all, I better tell you about the Southern Cross that we have up there, because that becomes to its highest point in the sky. Southern Cross never sets from our latitude here in the Wairarapa. It's always going to be in the sky somewhere. It moves in a great circle around the South Celestial Pole, grazes the horizon, and then comes up again. So at this time of the year, it's at its highest point in the sky. And you can always identify the Southern Cross by the two bright stars which follow it around, called the pointers. Right, so there's the two pointers there. And Jupiter you just look into your left, you're going to see Jupiter there as well. Now, Jupiter is actually quite a magnificent object, and even in a small pair of binoculars, if you catch Jupiter early enough before it gets too dark, you'll see that it's got like four little stars spread out alongside it. And from night to night, you'll notice the positions of these stars change. They're actually the moons of Jupiter that we're actually looking at. Well, when we look at Jupiter, and I remember when I was a kid, used to think of Jupiter as a planet similar to the Earth, but it's not. In fact, you could fit 1,300 Earths inside Jupiter. And furthermore, when we look at Jupiter, we never only ever see clouds. It's the patterns that we see on its surface are continually changing, but there's these big belts, these brown and white belts, but they're of enormous size. And what we're simply doing is looking at different cloud layers. So the white layers are like cirrus clouds that we have here on Earth. And when you look at the brown areas on Jupiter, you're looking deeper into the planet. But this planet has no solid surface at all. It's completely alien compared to the Earth. It's made, in fact, it's far more similar to the Sun. It's made of hydrogen and helium gases, which are pretty poisonous to us. And as you go down into the interior of Jupiter, you'll see that different structures. Now, one of the most famous structures that we can see on Jupiter, you can often pick it out, depending, normally it's there sort of 50% of the time, is what is known as the Great Red Spot. And this was named by Galileo. And there seems to be a spot. It's, in fact, a gigantic cyclone that's been raging for thousands of years, probably. We know it's simply been raging ever since Galileo had a look at it. But this cyclone is bigger than the Earth, so it's actually just quite a spectacular object. And sometimes the moons of Jupiter will pass by it, and you get these wonderful images, gives you a good idea on the size of it. Anyway, if we were to travel into Jupiter, we go down and eventually get completely darker. Very, very violent storms on the surface of this planet, but it has no solid surface as we know it. Eventually, as you go down beneath the cloud tops, you'll come to an ocean, but not an ocean of water. This is an ocean of liquid hydrogen, all right? So quite a weird world, ammonia and so on. And this ocean is 20,000 kilometres deep. You see, under the enormous pressures, hydrogen and helium begin to behave like liquid, all right? Of course, with any known spacecraft, we could never survive the journey to the ocean, because by that time, no known substance could hold up against the enormous pressure, so you'd be simply squashed out of existence. Now, Jupiter is in fact like a miniature sun, because it actually radiates more energy than it actually receives from the sun itself. And when you look at it, it's like a miniature sun with its own planetary system. It's got more than 60 moons. It's also got a system of rings, which we discovered, we can't see them very well from the Earth, but they were discovered by spacecraft. But 4 of the moons, called the Galilean moons, are interesting because they are the size of small planets, and they're actually quite spectacular objects. And again, when you use the word moon, you immediately think of, something like our moon, right? But in fact, these worlds orbiting around Jupiter are nothing like our moon whatsoever. The one that's closest to Jupiter is called Io. And Io is a world of fire. It is the most volcanically active world in the solar system. There's never less than about 3 volcanoes erupting on this planet. And its surface is absolutely pockmarked. There's no craters or anything like that. The whole thing is covered with yellows and white sulphurs. If you've been to Rotorua and you look at all the sulphurs, and that's exactly what the surface of Io looks like. And it's continually changing, and in fact the entire surface of Io is nothing there more than 1,000 years old. Now, you've got to remember, when you look at the Earth, most of the rocky surface we're looking at is millions of years old, in some cases billions. But Io is nothing there, is more than about a few thousand years old. And that's because there's so many eruptions. The face of the surface is continually changing. And this became as a bit of a surprise to scientists, because, first of all, how come a little world, because it's bigger than the moon, but certainly about, smaller than Mars, how could it be so volcanically active? Well, the answer is, as Io orbits around Jupiter, the other moons tend to pull it off as they go around, pull it off track, and so you've got this sort of tug of war occurring, and the inside of Io is tending to get squashed and pulled, and this generates an enormous amount of temperature, heat inside the little moon, which then turns into volcanic activity. So this is what we call sort of tidal flexing. And so in this case, volcanic activity, unlike the Earth, which is due to the internal heat of our own planet, the volcanoes on Io are all due to the tidal effect of Jupiter and the other moons. Then next out from Io, we've got another world. The next world is Europa, and it appears to be virtually the exact opposite, because Europa is a world of ice. So we've gone from fire to ice. But furthermore, when we look at the surface of Io, we see sheets of ice, but they're all broken up. It's not like just a simple solid surface. We can see great cracks, and in parts of it look like a jigsaw puzzle. The sorts of things that we'd see in Antarctica, where ice floes melt and then they refreeze, and you can see all the bits have frozen up together again. However, this is actually telling us something about Europa, because the fact that you've got this icy surface, but it also is telling you there's liquid water underneath, which is indeed there is. So beneath that ice is an ocean of water. And the other interesting thing, when we're looking at Io, you can see all these cracks on its surface where the main fault lines go along the ice, but there's this brown discolouring. And it turns out that that brown discolouring is actually due to organic molecules. And many scientists now believe if we're going to find life anywhere in our solar system beyond the Earth, Europa is going to be the most likely place we're going to find it. So beneath that ice, there appears to be an ocean. It's warm, again due to tidal flexing, and so it may well be supporting quite a amount of life beneath the surface in these oceans beneath there. And in fact, we're also interested in it. NASA's planning to send a spacecraft to Europa to land on its surface, bore a hole through the ice, and then send a little submarine down so we can check out exactly what's underneath those ice flows down there. Yeah, so Europa is a really, really interesting object. Now, moving outwards a little bit further, we come to Ganymede, and which is the biggest moon in the solar system. It's bigger than the planet Mercury, and I always call it the crystal planet, because it's out there. The surface of Europa is icy again, rock and ice, but out here at this depth from the sun, water ice takes on as dry and as cold as glass. So if you get a piece of water out there near where Jupiter is, it's not much different from glass. And so the surface of Ganymede is like a big plate of glass with all these different patterns that you can see underneath it, and so on. And finally, of the four big moons out there, we come to Callisto. And Callisto has got more craters on its surface than any other world in the solar system. Now, if a world's got a lot of craters visible on its surface, it tells you that the surface is very old. So we've gone from one end, which is Io, which has got no craters whatsoever, very, very young surface, to Callisto that's absolutely peppered with craters. Now, craters are created by impacts, things from space, little asteroids striking the surface. This happens everywhere, but of course, normally, like on the Earth, erosion wears these things away. But on Callisto, it looks like it has had no geological activity at its surface for about 4 billion years. So it's when we look at Callisto, we're seeing the record of all these impacts that have occurred over literally billions of years of time. So it's quite a spectacular world. And as you can see, each one of these worlds is very, very different. And that's just 4 of the more than 60 moons that's out there. Anyway, what we're going to do now is we're going to have a little bit of music, which we're going to be playing for you by Jim Woolsby, Galaxy Rise. And then when we come back, we're going to be looking at Olbers' Paradox. So that's what the plan is.
put it that on.
Oh, so hi folks, you're back with Richard Hall of the Night Sky, and what I wanted to talk about was Olbers' paradox. Now, Olbers was a cosmologist, mathematician, and he asked a very simple question. Sometimes simple questions have very profound meanings or behind them. He asked a simple question which said, why is the sky dark at night? And you might think, oh, well, the sky's dark at night because, you know, the sun's not there. But in actual fact, it's far more in that, because Olbers thought of it this way. He thought, well, you know, if the universe is infinite, right, then it goes on forever. And no matter where you look in the sky, you'll see a star or a galaxy, right? So therefore, his calculations showed that if the universe was infinite, then the entire sky would be as bright as the sun and we'd be just roasted alive. So therefore led him to the conclusion that the universe must be finite, not infinite. However, gravity tells us if the universe was finite, everything would pull together and the universe would collapse in on itself. So the universe wouldn't exist. A long, long time ago, it would have collapsed in on itself. So this is Olbers' paradox. Whether the universe is infinite or whether it is not infinite, either way, it shouldn't exist. But the answer to Olbers' paradox was one of the great discoveries about the nature of the universe. And so we'll be coming to that in a moment. So quickly looking up at our night sky, well, I want to talk about space and time, you know. In fact, I won't go into too much details now, but Einstein says space and time are exactly the same thing. But let's look at the scale of the universe. When we're measuring it, we often tend to use the speed of light, simply because it's the fastest thing known in the universe, all right? And roughly, rounding up, light travels at 300,000 kilometres per second. That means if I could travel at the speed of light, I could travel to the moon, right, which is 384,000 kilometres away. I could get to the moon in just 1 1/3 seconds. In fact, you could travel right the way around the Earth with the blink of an eye, all right, at the speed of light. Now, going out to Jupiter's a bit more further away. It's 1,400 million kilometres away, and at the speed of light, it would take you 1 1/3 hours to actually get to Jupiter. This, of course, means if you had some people living or in a spacecraft around Jupiter, if you sent a message out to them, said, "Hi, how's things going?" Well, that message would take over an hour to get there, and if they replied straight away, it would take an hour to get back. So you can't have much of a conversation once people get out as far as Jupiter. But these are just things inside our own solar system. The nearest star is one of those two-pointer stars, the Alpha Centauri, and light from there takes over 4 years to reach here, right? So we say that Alpha Centauri is 4 light years away, all right? And the further we look into space, the further back in time we look. You see, when we look at Alpha Centauri, we're seeing Alpha Centauri as it was 4 years ago. Jupiter as it was an hour ago. And as I said, the further we look into space, the further backwards in time we look. So we see the universe not as it is, but as it was. Now, the great galaxy which we're in, the Milky Way galaxy, is 120,000 light years in diameter. Contains something in the region of 150,000 million suns or stars. So there's literally, each of these has got planets, so there's going to be literally trillions of worlds out there just in our own Milky Way galaxy. And remember, even if you could travel at the speed of light, it would take you 120,000 years to travel from one side to the next. Okay, and we're on the outer regions of the galaxy, around about 26,000 light years from the centre. Now, our galaxy is part of what we call the local group, and it's a small collection of little clusters of galaxies. Our own galaxy is the brightest, the Milky Way is the brightest of about 20 or 30 smaller galaxies. And it's part of this local group which includes 2 other big galaxies, each with their own little clusters of smaller galaxies. These are the Great Galaxy in Andromeda, known as M31, and the Great Spiral Galaxy in Triangulum. But in turn, the local group itself is just what the universe is made up. These little tiny little groups of galaxies, all bound together gravitationally. Groups of galaxies about 50 to 100. But in turn, all of these little ones, like the local group, are simply attached gravitationally to gigantic clusters of galaxies. And ours is the Great Galaxy supercluster of galaxies in Virgo. And whereas our little local group only has 3 large galaxies, the Virgo cluster has over 2,000 giant galaxies, as well as literally thousands upon thousands of smaller galaxies. And the centre of this great cluster is 67 million light years away. All right? So that's how far we're looking backwards in time. Now, if you go out tonight and you have a look and it's nice and clear, you see the moon, and remember the sickle, well, just up to the right of the moon is the constellation of Virgo. And Virgo is actually a window for us into the greater universe, because looking away from the Milky Way here, we can see out to this great big cluster, the Virgo cluster in Virgo, 60,000 million light years away. And if you've got a big telescope, if you wander around there, you pick up galaxy after galaxy after galaxy. At the central region, there are gigantic spherical galaxies, while in the outer regions we have large spiral galaxies similar to the Milky Way, little clusters like that. But again, the Virgo cluster is just simply part of a great cobweb. It's like a knot, a cobweb of galaxies in the universe. And of course, one of the great discoveries made was the universe is actually expanding. All right. So in other words, that cobweb we're looking at of galaxies is gradually expanding outwards into space. And going backwards in time, as we look out there, right, we have now the answer to Olbers' paradox, because the sky is dark at night, because the universe is expanding. And the further away you are, an object is, the faster it's moving away. And eventually you reach a point where something is so far away, it's moving away at the speed, beyond the speed of light, so its light never reaches us. So the universe is dark at night because it is expanding, and that's the answer behind it. And I think we're just about running out of music right now, so I'm going to have to leave some of the other things till our next one coming up. Anyway, I say good night to you now, and I'll be back in a fortnight's time to talk about some of the other things in the sky.